We start this lesson off with the definition of what is extrema, and then we're going to talk about how we can use calculus to find extrema. So extrema are just extreme values. There's two different types. We can have a minimum, which would mean that the function value is less than all the other function values in a certain interval. Or we could have a maximum, which means that the function value at that particular point is higher, larger than, greater than all the other function values in that interval. So we can talk about extrema on an interval, like what we see happening in this graph here, because this graph here is stuck. We can also talk about extrema of the entire function if we're not working with an interval, and we can see like this function goes on forever in both directions. So there's two different types of extrema, and we'll specify which one we're talking about. There's relative extrema, and then there's also global extrema. In this section here, we're first going to be looking at global extreme. Global or absolute. Global and absolute can be used interchangeably. So when we look for the absolute maximum of this first graph here, we are looking for the highest point on the graph. Now, because this graph continues on up forever in both directions, there is no absolute maximum on this graph. However, this graph does have a lowest point. The lowest point on the graph is right here. I'll estimate this to be approximately negative 2.5, negative 35. So it does have an absolute minimum at the point negative 2. In our next example here, starting off looking for the absolute maximum, I'm looking for the absolute highest point that is on this graph. I can see that that's happening right here. This graph has an absolute maximum at the point 3,9. The absolute maximum value is 9, and it's occurring at the x value of 3. For the absolute minimum, I'm looking at the lowest point on the graph there. That's at the point 1, negative 1. So it has an absolute minimum at the point 1. In our third graph here, this graph drops down forever, and so this graph has no absolute maximum, no absolute minimum. It does, however, have an absolute maximum. It has two absolute maximums. Looks like we can see these 2 points right here. I'll estimate this one here at 2.13, and I'll estimate this one here at negative 3.13. It is possible for a graph to have more than one absolute maximum as long as they have the same y value, because it's possible to achieve the same y value at more than one point. So this graph is having an absolute maximum at both the points negative 3.13 and 2.13. So finding these absolute extrema is all about looking for the lowest point on the graph or looking for the highest point on the graph. And here's another example of a graph that has two absolute maximums. So in all four of these examples, we looked at the graph, we found the highest point, if there was one, and labeled it the absolute maximum, and we found the lowest point if it was one and labeled it the absolute minimum. Notice that when the graph increased without bounds, there was no absolute maximum, and when the graph decreased without bound, there was no absolute minimum. Next, we're going to look at the extreme value theorem and a couple of examples where we can apply it. The extreme value theorem states that if the function is continuous on the closed interval a to b, then the function has both a minimum and a maximum on the interval. So it has extreme values on that interval if it is continuous. It has both a minimum and a maximum. So here in example 1, we're given a polynomial function, and we're given a closed interval from negative 3 to 3, and we're asked to approximate the extrema using a graphing calculator. I'm going to use Desmos, but we could also do this on a TI-84 or a TI-83 by putting this function in our y equals. Notice that because f of x is a polynomial, it is continuous everywhere, and so the extreme value theorem does apply. So I went ahead and I've graphed this function off to the right on Desmos. The graph looks a little strange right now, so I'm going to zoom out until I see something that makes a little bit more sense. And this does make sense because we know this is a third degree polynomial. What we have to keep in mind of is that we're looking for extrema on the interval from -3 to 3. So we don't want to pick anything that goes any further left of that blue line, x is equal to -3, and we don't want to pick anything that goes any further right than that green line, x is equal to +3. And luckily, both of these extrema that happen here, this minimum and this maximum, are both on the insides of those two vertical lines. So I've written down where we have our max and our min at. I'm now going to do the same thing with this second function, which is f of x is equal to x to the third minus 3x squared. Notice that this function does not give us any intervals, so I don't have to graph any vertical lines. You can see this graph right here. I can see we have a relative maximum. There's a max happening right there at 0, 0. And then there's a relative minimum happening down here at 2, -4. Now, when I use the terms relative maximums and relative minimum, what I mean is that the graph at those points is extreme relative to the points near it. So when we look at this graph at what's happening at 0, 0, this point right here is higher than all of the other points on the graph that are surrounding it. It's higher than all the points around here. So this point 0, 0, or you could also call it a local maximum. Similarly, this point down here at 2, -4 is lower than all of the points that are around it, all of the points that are local to it. And so the point 2, -4 would be a relative or a local minimum. Because this graph increased without bound and decreased without bound, this second example right here has no absolute maximum and no absolute minimum. It does, however, have a local max at the point 0, 0, and it has a local minimum at the point 2, -4. So now that we have introduced the concept of local maximums and local minimums, here we have the formal definition of them. And the definition in these two lines summarizes what we discussed was happening at these 2 points. How the point 0, 0 was higher than all the other points around it, and how the point 2, -4 was lower than all the other points around it. Generally speaking, relative maximums are the hills that we see in the graph, and relative minimums are the valleys that we see in the graph. And the words relative and local are used interchangeably. But note that relative extrema cannot occur at endpoints. And so what I mean by that is if we have a graph, and let's say that the highest point on this graph is happening at an endpoint right there, even though this is the highest point on the graph, this is not a local max, because in order for it to be a local maximum, it had to be higher than all of the other points around it on both sides. And there is no right side to the graph of this, because the graph ends there. We could say that it is an absolute max, because it is higher than every other point on the graph, but it is not higher than every other point that is near it, because there are no points to the right that are near it. So we do not say that we have local or relative extrema at endpoints, but we can have absolute extrema at endpoints. Because of the nature of relative extrema, because they are the hills and the valleys of the graph per se, it must be true that the derivative at any extrema has to be equal to 0 or cannot exist. If we look at this example here, we can see we have a relative maximum here, and we also have a relative maximum there. And yes, that relative maximum is also an absolute maximum. But the point is, if I were to draw the tangent line in at these relative extrema, or at these extrema in general, I can see that there is a horizontal tangent line at those extrema points. So what that means is that the derivative is equal to 0 when x is equal to 2. The derivative, well, I think we said that was about 2.1. So the derivative is equal to 0 when x is equal to 2.1. And the derivative is equal to 0 when x is equal to negative 3.1, because we know that the derivative is the slope of the tangent line. Similarly speaking, down here we have a relative minimum at what I will estimate to be about negative 0.5. Because again, we have a horizontal tangent line there, I could say that the derivative at negative 0.5 is equal to 0. So the point of all three of those points, the examples that we wrote there, is that the derivative equals 0 at extrema. So if you want to find extrema, we should find where the derivative is equal to 0 at. Or, because if we look at the example on the right-hand side, go ahead and label my x and my y axes, we do have an absolute minimum right there happening at x is equal to 0, but the tangent line at x is equal to 0 would be a vertical tangent line. That tangent line is undefined. We've talked about the absolute value function and how the derivative does not exist at sharp corners. So we do have a relative extreme. We have an extrema happening there at 0. We have an absolute minimum. It's also a relative minimum. Please don't get confused thinking about whether it's absolute or whether it's relative. The point is that it is a minimum and the derivative does not exist. So when we start our search for extrema, we're going to be interested in where the derivative is equal to 0 and where the derivative does not exist, because those are the two places where it is possible that we have extrema. And those two values, where the derivative does not exist and where the derivative is equal to 0, are so critical to our search for extrema that we call them critical numbers. Critical numbers are the x values, where the function is defined, where the derivative either equals 0 or does not exist. Those are the two conditions that we have in order to be a critical number. Well, really the three conditions. It had to be in the domain of the original function, the derivative can equal 0 there, or it cannot exist. We've already discussed how extrema can only be happening at critical numbers. So here in example 3, we're being asked to find the critical numbers of this function. We are being asked to find the critical numbers on this particular interval, so we don't want to choose any numbers that go outside of that interval. So to find the critical numbers, we are going to have to come in and find f prime of t. We need to take the derivative and look for where the derivative does not exist or where it is equal to 0. To find the derivative, we're going to have to use the product rule. So I've written my f and g for the product rule. I'm going to rewrite g in a way that's going to make it easier for us to take the derivative of it by writing it to the 1/2 power. I'll come in and take f prime, which is 2t, and then I'll come in and use the power rule to take g prime, and we're also going to have to use the chain rule. And then I'll simplify the derivative of g prime. This 2 will cancel with that 2. We're left with a negative t in the numerator over the square root of 3 minus t squared. Now that we have all 4 of these components, we're able to come in and actually apply the product rule, f prime g plus g prime f. So we have 2t multiplied by the square root of 3 minus, I'm going to write this to the 1/2 power of 3 minus t squared to the 1/2 power plus g prime f. Well, g prime is negative, and so I'll just make this a minus sign. I have t, this is g prime over 3 minus t squared, and this needs to be multiplied by f, and f is t squared, so I'm just going to put a t cubed in the numerator because I'm multiplying that by t squared. So from this point, we are looking for 2 sets of values. We are looking for sets of values where, I'm going to draw a vertical line here. We are looking for sets of values where the derivative does not exist, and then we're looking for sets of values where the derivative is equal to 0. The derivative would not exist anywhere where the denominator was equal to 0. Well, the only denominator that shows up is this denominator right here. square roots are only going to equal 0 if what's on the inside of them is equal to 0. So I'll set this equal to 0, and then I can quickly solve this by adding t squared to both sides and getting that t is equal to plus or minus the square root of 3. Both of those functions are included in the domain of our function. They were included in our interval, so both of these so far are critical numbers. We found two numbers where the derivative does not exist. Now I'm going to go look for numbers where the derivative is equal to 0. So I'm going to take the entire derivative, which is 2t, 3 minus t squared to the 1/2 power. And I think that one, I'll just write it as a square root now. Minus t cubed over the square root. All of this is set equal to 0. I'm going to add the t cubed term to the other side of the equation. And then I'm going to multiply both sides of my equation by this denominator in the square root. By the square root that's in the denominator so that we can get rid of it. It will cancel on that side. And on the left side of the equation, when I multiply this in, it'll be like squaring that, and it'll cancel the square root and just leave us with a 3 minus t squared. So now I'll distribute on the left-hand side of this equation. I have 6t minus 2t cubed is equal to t cubed. We'll get 0 on one side, and I'll set both of these factors equal to 0. The first one is already solved. The second one, I'll need to add 3t squared to both sides of the equation, and then I'll divide both sides by 3, and then I'll take the square root of both sides and remember to do plus or minus. And so we have found 3 numbers where the derivative is equal to 0 and 2 numbers where the derivative does not exist. So all in all, the critical numbers for this function are negative root 3, negative root 2, 0, positive root 2, and positive root 3. Do note that the only reasons why we're including these 3 down here, and really all of them, is because they do fall into that correct interval. We're going to start off example 4 by taking the derivative s prime of theta. We're taking the derivative of tangent squared, so power rule says we bring the exponent of 2 down in front of tangent, and then chain rule says we multiply by the derivative of tangent, which is secant squared theta. From that, we are subtracting the derivative of cosine theta, and the derivative of cosine theta is negative sine theta. So we are left with 2 tan theta secant squared theta plus sine theta is equal to, well, I'll stop here, not equal to anything. So this is s prime of theta, and I'm going to rewrite this derivative in terms of sine and cosine. I think that's helpful because we need to find out where this derivative does not exist, and so we're interested in where the denominator will be 0. So I've rewritten tangent as sine over cosine, and now I'm going to rewrite secant squared as 1 over cosine squared. So just one final rewrite of this will be 2 sine theta over cosine cubed theta plus sine theta. And then the two things that we are interested in from this derivative to find our critical values is from this whole derivative, we are interested in where it either does not exist or where it is equal to 0. To find where it does not exist, that would be where its denominator is equal to 0, because fractions do not exist where their denominator is 0. So I can drop the cubed by cube rooting both sides, and I'm just then interested in where is cosine equal to 0 on this interval from 0 to 2 pi. If you need to sketch or reference a unit circle, do that to see that cosine is equal to 0 at the radian measures of pi over 2 and 3 pi over 2, because cosine is the x coordinate. So for the two places where the derivative does not equal 0, or where the derivative does not exist, are pi over 2 and 3 pi over 2. And remember, we're only working in this interval here. Now we're going on to look for where the derivative is equal to 0. So I'm going to take the entire derivative function and set it equal to 0. I'm going to subtract the sign. Actually, I'm just going to go ahead and multiply everything in this equation by cosine cubed so that I can get rid of the fraction. So I'll have 2 sine theta plus cosine cubed theta sine theta equal to 0. Because this is already set equal to 0, I'm just going to go ahead and factor out a sine theta because that shows up in both terms. So I'm left with a 2 plus cosine cubed theta is equal to 0. So now we're going to set both of our factors of sine theta equal to 0 and 2 plus cosine cubed theta equal to 0. The first equation is already solved. The two places where sine is equal to 0 that are between 0 and 2 pi, because remember we're still working in that interval, are at 0, where sine is 0 because sine is the y-coordinate, and at pi, where sine is 0 because sine is the y-coordinate. So the two answers we get here are 0 and pi. And then over here, I'm going to subtract cosine. I'm going to subtract 2 from both sides and get that cosine cubed theta is equal to -2. And then I'll cube root both sides to get that cosine theta is equal to the cube root of -2. But the cubed root of -2 is a number that is smaller than -1. This is approximately -1.259. And we know that it's not possible for cosine to be smaller than -1. So that factor does not give us any solutions. So the possible answers we have for critical points, and I do mean possible, are 0 and pi as the two places where the derivative is equal to 0, and pi over 2, 3 pi over 2 as the two places where the derivative does not exist. But one thing we need to be careful about in this example that we didn't have to be careful about in the first example is that in order for a number to be a critical value, the function has to be defined there. So in the first example, we didn't have to worry about that because they gave us this interval, and this interval is exactly the domain of that function. So because all of our numbers fell into the domain of that function, we knew that they would all be defined. Now in example 4, we know that this is not the domain of this function, right? We're only being given this interval because that's one full revolution around the unit circle. The function that we started with in number 4, s of theta equal to tan squared minus cosine theta, is the same thing as sine squared theta over cosine squared theta minus cosine theta. So we know that s of theta is undefined wherever the denominator would equal to 0. And in the denominator we have that cosine squared. So the function is undefined wherever cosine is equal to 0. And cosine is equal to 0 where the x-coordinates equal to 0 on the unit circle at pi over 2 and 3 pi over 2. So these values that we got over here are not even in the domain of our function f. And so these are not included as critical values. Only 0 and pi would be our critical values. So critical values have to be in the domain of the original function. We still needed to do this work to figure out where the derivative did not exist. It's only once we get those values that we can say, hey, those values are not in the domain of the original function, and so we are not going to include them as critical values. The last thing we're going to talk about is how to find absolute extrema of a function on a closed interval. We begin by finding the critical numbers because we know that extrema can happen on the interior at critical numbers. Then we're going to evaluate each critical number in the original function. So please note that numbers 2 and 3 we are plugging into the original function because we're interested in the highest point on the original graph and the lowest point on the original graph. Number 3 tells us that it's not sufficient to just evaluate the function at critical values. We also have to evaluate the function at endpoints, and I want to draw a picture to show you why. Let's say we have a function on some closed interval from A that starts here and then goes to B right here. Well, we can see that we will pick up some critical values in between, because I do have some places where the derivative is equal to 0 and we have some relative extrema. So those 3 x values right there, and right there will be included as critical values, which I'm just abbreviating as CV. But what number 3 is telling us is that we also need to make sure to check the endpoints, because it might be possible that the endpoint is the highest point on the graph. Because if we never check the endpoint, we might think that this is the highest point on the graph when it actually isn't. It's actually happening at the endpoints. Number 4 just tells us that the smallest number we got is the minimum and the largest number we got is the maximum. So let's jump in and look at example 5. We want to find the absolute, well, all of the extrema on this interval. So we begin by taking g prime of x. I'm going to use the power rule. Now that we have g prime of x, we're going to look for its critical values. Critical values are the places where the derivative either does not exist or where the derivative is equal to 0. Our derivative is a polynomial, and so it always exists. It never happens that there's anywhere where the derivative does not exist. But we can find some values where the derivative is equal to 0. I'll start by factoring out the GCF of 12x squared. And now I will take both of these factors and set them equal to 0 to get that x is equal to 0 and that x is equal to 1. So those 2 values right there are my critical values. So now that we have our critical values and our endpoints, we're ready to go and make a table of values that are going into the original function, which is called g of x, not f of x. And in this table, we want to plug in our endpoint of -1, the critical value of 0, the critical value of 1, and the endpoint of 2. And the values that I've gotten out for -1 are 7, for 0 is 0, for 1 is -1, and for 2 is 16. So what I can definitely say is that the greatest number of 16 is the absolute max. So I know we have an absolute maximum happening at the point 216, and the least number of 1, -1 is the absolute minimum. But we need to confirm that with a graph. And so I've graphed this on Desmos, and I'll pull the graph over here. Notice that when I graphed this function, I did make sure to include the restrictions of -1 and 2, because we're only looking on that interval. So I'm not looking past that point -1,7, and I'm not looking past this point 216. We can also see down here that we do have this absolute minimum at 1, -1, but points like this are why we need to make sure to confirm the graph, because at 0, 0, yes, that is one of our critical values, but we can see that we do not actually have any extrema happening there on the graph. It is a place where the derivative is equal to 0, but there is no extrema happening there. So let's continue and find our relative extrema. We can see that the point 1, -1 is also a relative minimum because it's lower than all of the other points that are around it. It is a valley on the graph, but there is no relative maximum on this graph because there's no hills on this graph. Now let's come in and look at example 6. I'm going to change this independent variable there to x to stay consistent. We'll come in and start taking our derivatives. The derivative of 2 cosine x is -2 sine x. And the derivative of negative sine 2x is -2 cosine 2x, where this 2 on the outside is coming from the chain rule. This 2 on the outside is the same 2 that was already there. So now that we have this derivative, we are now ready to go look for critical values. We're looking for places either where the derivative does not exist or where the derivative is equal to 0. Sine and cosine functions exist everywhere, so we don't have any places where the derivative does not exist. But we do need to come in and take this derivative and set it equal to 0 to solve this trig equation. Now, solving this equation, we can see the equation has sine in it, and the equation also has cosine 2x in it. In order to solve that, we're going to have to use an identity to replace the cosine 2x in it. One of the double angle formulas we learned in 172 was that cosine 2x is equal to 1 minus 2 sine squared x. There's 3 options for that formula, and I chose to use the one that only had sine in it. Now I can finish simplifying this equation. I'm going to rearrange the terms just so it looks a little bit more familiar, like a quadratic equation. Everything has a 2 in it, so really from early on we could have divided the entire equation out by 2. So now that we have this quadratic equation nice and simplified, if it's easier for you, you could do something like let a equal sine x. That's the same technique we used in 172 when we were solving trigonometric equations, just so that it looked a little bit neater. Then we can come in and finish factoring this equation. This factors into 2a plus 1 times a minus 1. You could also solve this using the quadratic formula. We then go in and get our 2 roots, that a is equal to negative 1/2 or a is equal to positive 1. And we remember that a was sine x. So we are looking for where sine x is equal to negative 1/2 or where sine x is equal to 1. At that point, we go back and we remember our unit circle, and we know that sine is equal to a negative 1/2 at 7 pi over 6 and 11 pi over 6. Those are the 2 places where the y-coordinate is negative 1/2 on the unit circle, and the only place where sine is equal to 1 on the unit circle is at pi over 2. And so we have 3 critical values in this problem here. So to test and find our extrema, we need to make a table where we include our endpoint of 0, our 3 critical values of 7 pi over 6, 11 pi over 6. I think I'm going to make my table run horizontally so that it will all fit. All of these x values are being plugged into the original function. So I have 0, 7 pi over 6, 11 pi over 6, pi over 2, and then our final endpoint at 2 pi. And all of these we will be plugging into the original function, looking for the maximum and looking for the minimum. So when we plug in 0, we get out 2, and I'm just evaluating this using a unit circle. When I plug in 7 pi over 6, we're going to get out negative 3 root 3 over 2. When we go on to plug in 11 pi over 6, we're going to get out a positive 3 root 3 over 2. When we plug in pi over 2, we get out 0. And when we plug in 2 pi, we get out 2. And so the maximum value that we got out is the 3 root 3 over 2, because that's a little bit bigger than 2. That's about 2.59. So our absolute max, or our global max, is happening at 11 pi over 6, 3 root 3 over 2. Our global minimum is going to be at the negative 3 root 3 over 2, where the x-coordinate was 7 pi over 6. And then I am going to pull up a graph just to confirm these values. So looking at a graph of this function here, we can see that we do have, and I notice I do have my 2 vertical lines at 0 and pi graphed. I do see this global min down here at 7 pi over 6, and this global max right here at 11 pi over 6. Those are the highest and the lowest points or the lowest and the highest points that are between the black and the red lines. And if you notice, both of these points, the absolute max and the global max, they're both relative extrema. This is also a relative max and a relative min because they are hills or valleys respectively. So I'll copy those over into the local max position and the local min position.